Hi all, this is the pre-class video for the Bridgeports here at MakeHaven. These are vertical milling machines. There are horizontal, there's other kinds of milling machines. So this is a vertical kind, it's oriented up and down. And milling is removing metal sideways, especially. It can go up and down too, like a drill press, but vertical milling machines, really are specialized in going sideways. So it's really a super fancy drill press. Bridgeports were made in Bridgeport, Connecticut, and are known around the world as, it's sort of like Kleenex, like you say Bridgeport when you're referring to a vertical milling machine. So that's pretty cool. These two were actually made in Bridgeport, Connecticut. And we're gonna run through all the basics that you need to know for using them so that when you take the class, you can jump right in and start using your hands. So we're gonna start with like the basic anatomy of the tools. So we'll start here with the bed. So the bed on the Bridgeport is a very important surface. It's a precision surface, so it's important that you're gentle with it. You're not dropping tools, you're not scraping it up. Definitely don't drill or mill into it, because the accuracy of this machine, and this is meant to be a fairly precise machine, is resting on this bed. So you mess that up and kind of the house of cards tumbles from there. So the bed moves in the x-axis. X means left and right, with these hand cranks. On the hand cranks are actually micrometer meters, which is pretty cool, so we'll get into that in a little bit. And then the ways for the x-axis rests on the knee. This is the knee of the Bridgeport. Sometimes it's called a knee mill for that reason. And there are ways here too. So these dovetail ways, because you can see they have this dovetail shape, are what the y-axis rides on. And the y-axis is forwards and backwards. As you go forwards and backwards there's also the micrometer gauge that you can see on this dial. The knee mounts onto the trunk of this vertical milling machine. And then on top of that, we have the turret. So the turret is kind of this whole assembly, and you can turn side to side. And you can see the dials on here. So if you're doing something crazy, you could, in theory, turn it 180 degrees all the way around. Then, if you wanted to move that position, you'd loosen these 4 bolts, these 2, and the 2 on the other side. And then you'd be able to turn it. Then you have the ram. So the ram is this piece, and the ram can move forwards and backwards. So to move that, you would loosen these 2 bolts, and then this handle actuates it forwards and backwards. Move that light out of the way. Then over here, we have sort of the head and the spindle assembly. This is called the quill. So the quill is the piece that holds the tool, and it goes up and down. And then this handle moves the quill up and down. Here we have the head, and this is a pulley Bridgeport. We'll look at the variable speed Bridgeport in a minute. That means it has pulleys to adjust the speeds. So depending on how fast you want to go, based on your material and the end mill type, you can adjust those speeds. The motor is up in here, and this whole head assembly can tilt forwards and backwards to get angles like that, and tilt this way. So to tilt the head forwards and backwards, you loosen these 3 bolts, and then right up here is the bolt that you would turn with a worm gear on the end to tilt it forwards and back. These are all 3/4 inch bolts. And then to tilt sideways, you can loosen these 4 bolts on the front. They're actually nuts, the 4 nuts on the front, and then turn this bolt with a worm gear on the end to tilt sideways. So that's pretty advanced. In general, we just leave it in this kind of squared up position. An important note is that if you do ever choose to change any of those orientations, it's very important that when you're done, you put it back to exactly 0. You need to make sure to do what's called tramming the head. We'll cover that later, just to make sure that you're not messing up the next person. So when you put it back, it's got to be dead square. Another important set of handles that we're going to look at here are the locks, the way locks. So when you're milling something, you want to make sure that you're only moving the axes that you want to move and not the others. So let's say we were moving along the y-axis in and out and didn't want the x to move. you'd need to make sure to lock this. So you would turn this with an Allen key, tighten it, and now it won't slide. When you're done, make sure to unlock it so the next person isn't grinding the ways, unsure why it's so stiff. So make sure to loosen those when you're done. The lock here is for the Y-axis. You would tighten that. And again, make sure to loosen it when you're done. And then for the knee, going up and down, is this. So we'll make sure to tighten that and then loosen it so that it can move again for us. We will look at some of the controls on here. So it has a control box, same as all the other tools. You swipe your card, push the button, it turns on. There's an e-stop right front and center. So if there's an emergency, you can push that. If the tool isn't turning on for some reason, that could be the reason. Then we already looked at the handle to pull out the quill, to pull down the quill. Here is a depth stop. So let's say you wanted it to go to a certain depth on this meter and stop right there. Then you could lower it to that position and then turn this jam nut so it stops when you pull it down to that position. So that's pretty cool. Let's say you're going down, and similar to the locks on the other axes, you wanted to lock this axis. You pull this down, and now the quill lock is engaged and it won't move. Turn that back up. Then up here, this is, remember where the pulleys and motor are. Let's say it's going and you want it to stop more quickly than it's slowing down on its own. You can push this is the brake, and you don't want to go too crazy with it, but you can brake the motor, the spindle, just like that. This is for changing from high to low gear, which we'll look at. And then most of these other handles are for controlling the quill feed up and down, which is a kind of advanced feature we'll look at in a few minutes. So we'll look at changing speed on this tool and then on the other Bridgeport in a minute. So to change the speed on this Bridgeport, and this is the one with pulleys, we obviously make sure it is off first. You could push and e-stop just to make extra certain. And then you loosen these clamps on either side, so this one, and then I'll get the one on the other side. Loosen this guy, and now the head of the motor is able to move like that. So it pivots so we can change the pulley speed. So let's say we wanted to go faster, we wanted our end mill or tool in there to spin faster, then we would have a bigger pulley position, which is lower down on the back side, and a smaller one on the front. So in general, it's easier to go to the smaller one first. So we go to smaller in the front, and then bigger in the back. And now we're in a higher speed. And we can see what speed that is on the chart on the front of the machine, which is right here. So on this, there's two gears, high gear and low gear. And if we're in low gear, which is slow, it's this top row of speeds. And 80 would be the slowest speed if the belt was in the highest position, and 325 would be the fastest if the belt's in the lowest position. And then if we're in high gear, 660 is the top set of pulleys, 2720 is the bottom set of pulleys. Now that we've changed the pulley position, we want to make sure to retighten the belt. So we're going to go over to this side, and we're going to push back on here to make sure that the belt is taut, and then tighten this so it can't move, and you can push on the belt just to make sure it's nice and taut. We have a step stool floating around if it's helpful to get up there, and then this one we just tighten it. Now let's say we wanted to change from high speed to low speed, high gear to low gear. There's a little instructions right on here. So let's say right now we're in low speed and we want to switch to high speed. So high speed, move A to the front position. So this guy, we're going to move to the front position. Keep B at in position, which is to the left, which is low speed, because that's what we're in, and we're moving out into high speed. Then the next step is move spindle pulley until clutch drops into mesh. And then I'm going to turn this pulley until it drops into position like it said. So just like that. So it plunked into position. Now the next step, and then it says if pulley can't be moved, clutch is already in mesh. So that's good. Now move B to the side position. So B is this. We're going to move over to the side position, which is high. Good to go. And now we are in high speed. And because we put the belt in the lowest position, we're in really high speed. So we're going to switch it back to low because we don't want to be quite that fast. So low speed, move A to the side position. So just like that. Move B to the in position, like that. And then we'll just turn this, make sure everything's happy. Because you need to, sometimes it isn't quite meshed in gear. So you need to turn the pulley just to make sure everything's happy. Now we will look at changing the speeds on this other Bridgeport. So this other one is much easier. And the way that you change the speeds on here is to change just the speed that you're running at in that same gear. You just turn this crank, and like it says, caution, do not turn unless motor's running. We're not going to turn this because the motor is not running. We can only turn this when it is going. But we can change from high to low gear. So right now, if you look on the side, we're in high gear. If we go like this, we're in neutral. So it's just spinning freely. It's not engaging the motor. And then going like this puts us in low gear. Couldn't be easier. And then once you're in whichever gear you want, then you just turn this and it says low range, this is your speed. High range, this is your speed. Super convenient. The brake is here on this one. Other than that, pretty much the same. So we'll go back over to the fully Bridgeport. And here, again, this is the same for the on-off switch. If you are in high gear, then going up would be forwards. And if you are in low gear, then I'm trying to put this off. So high gear would be forwards, and low gear would be forwards this way. Obviously, if you want to spin reverse, you just push it the other way. So since right now we're in low gear, that would be forwards. So you just need to make sure you're lined up with which way you're going. So let's look a little more closely at these micrometer dials on the sides. So let's say we had our piece lined up and we're right here at 0 and we wanted to go 0.2 inches. Then what we would do is just rotate, turn, 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 turn until we're at 120. This is in thousandths of an inch, which will make sense if you've watched the metrology video. So 0.14, 0.15, 0.16, 0.7, blah, 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 until we get back to 0. That's 0.2 inches. But that's assuming that we're already lined up perfectly with our piece. But let's say we just randomly found the side of our piece. Now we loosen this jam nut, set it to 0, just like that, lock the jam nut, and now we've just set our 0 at the edge of the piece. And then we could go to, say, 12 thousandths. That would be 10, and then 11, 12. So that's how you use those dials. Now, something that this system struggles with is backlash. So backlash is when we have a long lead screw, which is just a long bolt inside of here, and it's meshing with the nut, and the two aren't perfectly matched. And so this is really good, but if you look really closely here, you can see that there's a little play here. So I'm turning the handle and it's not moving. And it's moving like 3 thousandths of an inch. This might be bigger here. Yeah, so here's a lot of backlash, right? I mean, that's like 1/8 of a turn and it's not doing anything. So let's say you get it lined up with your number and then you go the other way. Well, now you have a whole chunk of turn that's unaccounted for, and that's called backlash. And so the way you account for that is just make sure you either always go in the same direction, and if you change, you just need to make sure to reset the dial to the actual position. So that's confusing. And so what we have now in 2022 are digital readouts, or DROs. And so the DROs are reading through glass scales, which you can see on here. That's what these things are on each of the axes. X, Y, and Z is down here. They read the actual position of your bed. So here, when I turn this hand crank, you can see the X position moving to the thousandth of an inch. And that's awesome, because now we're not worried about backlash. Here, like this is the backlash, I'm moving in the handle, and it's not changing the number. So that's great. Let's say, just to do a brief run through the DRO, we got to the side of our piece, we would hit X0, now that's zeroed out, and now everything from there is positive. Similar Y, 0, and then moving this way is positive on our piece. Let's say we were cutting this piece of material. The coordinate system thinks that we start at the bottom left corner of our piece. So that means that X positive is this way. So if we go this way, this is X positive. If we go up on our piece in the Z axis, if we go up, it's actually bringing the knee down, but it's up on our piece. So bringing this guy down is Z positive, and Y is positive going this way towards the back. So now the Y is going up. So that's how the coordinate system works on these vertical milling machines. So let's look, just because we're at the vise right now, at how work holding works. So work holding is when you're talking about how you hold your work piece. And there's a lot of different ways to do it. Here we have a vise mounted on here, and the vise is a great way of holding your work. This is called the fixed jaw in the back, and then this is the moving jaw in the front. So you want to put things in here, holding it in such a way that you have exposed the piece that you're actually working on, and then you're holding on to the piece that you don't need. Some tips for using this are we have parallels over on the table, and then for the other one they're on top of the cabinet. So we'll just look at these parallels. And the way parallels work is they're just sets of metal bars that are a certain height. For them to work well, they need to be clean. So you can grab a rag to make sure that they are totally clean. The rags live right over here. So we're going to clean the parallels off, because if there's a little chip of metal, it throws off all of your measurements. So we need to make sure they're nice and clean. And we're going to clean off the area here in the vise jaws so that that's not sitting on anything. Okay. And now the parallels we put in just like that. So they're sitting up against the sides, and then we take our workpiece. This is a clamp, please don't cut these actually, and then slide it right into here. So this is obviously holding it really low, but that might be good if we were drilling a hole or something and we, just wanted to get it up above the vise so that we could drill all the way through our piece without drilling into our vise. So here's the hand crank for the vise. And all right, so we're in. We're gonna tighten it just the teensiest little bit, and then make sure it's on the parallels and make sure they're sitting straight up. And we're gonna grab this tool. This is called a dead blow. It's called a dead blow because inside, it's a little hard to hear, it has lead pellets. And what that does is a normal hammer, if you hit it, it bounces up, but this just stops dead. And so what the dead blow is good for is stopping something from bouncing up. So here, we're gonna tap on our piece. Just gonna get it out of the way. We're gonna tap on our piece, and then the check is to see if the parallels move underneath. And the parallels shouldn't move. They should be stuck underneath there. And now the parallels are stuck, and that's how you know that it's in there. Then you can tighten the vise all the way to make sure that it's fully tightened and isn't gonna go anywhere. You can remove the vise handle to get it out of your way if you want. Also, as a note, this Z-axis, the knee handle, can be a little annoying, so you can just flip it on backwards when you're not using it so your leg isn't hitting it. Now there are other ways to mount to the Bridgeport for work holding, and we'll look at the next most common one, which are called step clamps. And step clamps are in the little container on the side here. So for using the step clamps, which are useful for a lot of holding operations, we grab a T-nut, and this is the clamp piece of it, and then a block. And you'll see, and also a bolt and a nut. So there's a bunch of pieces, and you'll see how they work on here. And generally, you'll want at least 2 sets of what I just grabbed. So let's say we're just trying to clamp this guy, then we can slide a T-nut right in here in the T slot, and then put a bolt into it, and then drop, we'll put this here, and drop this down here, and then we're going to take the nut and put that on top. You'll notice that I put this at a declined angle, so this is pointed down a little bit. If it's pointed up, the piece will just pop right out. So you want to point it down a little bit, and you want to put the bolt and the nut about as close to the workpiece as you can. So it has, a lot of leverage clamping down on it. So you would tighten that, and then your workpiece would be tight, and then you can square it up, do whatever you want to do. And in general, you would have multiple. Now this isn't necessarily the best fixturing for this piece, but that's just how to use these step clamps. While we're on the topic of work holding, let's go over to the shelves over here to see some of the other work holding options. So over here is another vise, slightly different style. This is a rotary fixture, so you can clamp down onto here using these T-nuts and then rotate your workpiece for doing circular things or things in a circular pattern. And then this is an angle vise, so you clamp your piece and then can tilt it at all kinds of weird angles if it's easier to do that than to tilt the head of the Bridgeport. Over here are some other work holding things. So these are called 1-2-3 blocks, and 1-2-3 blocks are 1 inch by 2 inches by 3 inches in dimension, and they're fairly precision tools, so make sure not to drop them or scratch them because they're supposed to be exactly that dimension. And you can use them to raise things up, to clamp to. They have some threaded holes to bolt into, so they can be useful for holding things in certain positions. These are V-blocks. So V-blocks are for holding circular things or maybe a square thing at a 45-degree angle. So they sit right there and then you clamp down on it. This is another set of small V-blocks. And then these are some angle plates. So if you want to have a 90-degree angle to mount to, then you can clamp this to the bed and then clamp to this face. So now we're going to look at all the different kinds of tools and tool holders. So just like work holding is how you hold the work, tool holding is how you hold the tools. And most of them are held over here. So these are collets. The way that collets work is by squeezing on this taper, so they get pulled up with a drawbar that screws into those threads. It pulls it up and then squeezes the collet on your tool. Each collet is labeled here with a size as 1/8 of an inch, and it only holds a 1/8 inch tool. Maybe a little bigger, a little smaller, but not much at all. Really, it's meant for that exact size, unlike a chuck. These are called R8 collets. They're different styles of collets. For the Tormach or for the Gerber and the wood shop, these are R8 collets. Then this is a chuck, which can be both keyed or keyless, and it has the same R8 taper on here. So this goes right up into the machine. You'll see the keyway, which is important. That gets held, and then you can hold drill bits in the chuck of any size. Right here is the key or the wrench for tightening this. And then this is what's called a Weldon shank tool holder. So this also goes up into the up into the quill using that R8 style holder, but then it has these 2 set screws. And so this is for especially large tools. You put them in here, and they have flats on one side that you can clamp down on to hold your tool. So that's just another style. So R8, 1 inch is the size of shank that this tool holder holds. There's a fairly similar setup on the other Bridgeport. The chuck here is a different style of key, but same idea. And now we will look at some of the tools. So in general, on Bridgeports, you use end mills. End mills are like drill bits, but they also cut sideways. So we'll grab just a pretty normal looking one to start with. So here is a carbide end mill. You can tell it's carbide because it's especially heavy for its size versus a high-speed steel one, which feels much lighter, as you can see in camera. And then the carbide versus high-speed steel, carbide is just much harder and can stay sharper longer. So in general, carbide is great to use, but certainly not necessary. We got by with high-speed steel for a long time. So this end mill, we'll just look closely right at the end. You see it? The end, you can see the flutes, those cutting edges, go all the way to the middle. So this is a center cutting end mill, which is important because this means it can cut straight down into the workpiece. Some of them don't have flutes in the middle. They just have them around the sides, and that means it can only cut sideways. And it's important to make sure you know which kind you're working with so that you don't make a mistake and just start melting things by pushing down into metal and not cutting it. This has 4 flutes, 1, 2, 3, 4. In general, for harder materials, you want more flutes so that each flute is taking off less material. If it's something softer like aluminum, you can have fewer flutes, like 2, and then each flute can cut deeper and take a bigger chip off as it's cutting at the same speed or at a different speed. On the side, it'll often say the size. So here it says 3/8, which might be hard to read, but I promise you it says it there. And that's why it lives in the 3/8 bin. Then, if you come take a look in here, we can see some of the other sizes and shapes. So some of them have flutes that are different size than the shank. Some are double-ended, so you can have 2 sharp ends to work with. Then there's no guarantee that any of these are brand new, so it's important to check it. You can even check it with calipers to make sure it's the size that it's advertised as. If it's been sharpened, it might be a little bit smaller, which is important to note. If you want your own brand new end mills, you're welcome to buy them yourself, obviously. Then, so these go from 1/16 up to 1 inch, and then we have just another set going from 1/2 up to really big, 1 3/4. These are drills, so fraction drills, letter drills, and number drills. These are just different ways of indicating the sizes. So you can see a little chart right here. We have some others hanging up on the wall that show the different sizes. So here you have like the letters over here. These are the number drills. So depending on what you need, you can use either fractional, letter, or numbers. And then these are some really special end mills based on their purpose. So here we have keyway cutters. So you could use this to cut a little keyway for a key to go in a shaft, if that's what you needed to do. These are called reamers. So reamers are meant for taking off just a little bit of metal. So if you want something to be a perfect size, so on here it says 0.5240. That's the size end mill, the size hole it'll make. Then what you would do is you would drill a hole using an end mill or a drill bit to something a little smaller than that, so maybe 0.520 or 0.2, and then you would follow up with the reamer, and that would get it to just the precise size. So reamers are removing very little material just to get it that last little bit. Then here we have taper end mills. So these are end mills that are at a taper. So those are, pretty special. And then these are dovetail cutters. So if you wanted to cut a dovetail in your piece, or maybe, chamfer something on the bottom. So there's different uses for that. Up here we have spot drills. So a drill, so we'll grab an example of a drill here, is fairly long and skinny and can deflect. So let's say you're trying to hit a point. What can happen is it can move around on you, and then it's not in the exact position that you want. This spot drill has a really big shank on it, so this is not going to deflect. It's not going to bend. So if you put it on that spot, it's going to start that hole just in that spot, and then you can follow up with a normal drill bit to make sure that you are in the correct location that you want it to be. So that's what a spot drill is for. And then these are countersink bits. So these bits are for making countersinks in holes, so that it has an angle on the edge of the hole for a fastener to sit down in or some other purpose. Now let's look down here. These are just larger size drill bits. These are different kinds of mills. So this is called a shell mill. And what it does is it has these carbide inserts. And so the carbide inserts are replaceable. We have them in the store if you want fresh ones. But they each also have 3 tips on them that you can use. So you could rotate it to the next tip if the one that you're using is dull. And these are good for cutting a wide area. So if you wanted to give something a flat face, then you could use it, for that. So that's pretty useful. And then this is called a fly cutter. So a fly cutter has this piece of high-speed steel in it, or it could be carbide, and it's spinning around fast, and it's for skimming off just a little material, but over a wide area. It has a big radius that it's cutting over. So you can use it for skimming the top of a thing if you're removing less material than you are with a big shell mill. This is, well, these are both, these are styles of boring bars. So there's a boring head, and you can mount the boring bars, which are these, in the boring head, either sideways if you want to make it a really big fly cutter, or in the top if you wanted to get to the inside of a hole of a very certain dimension. There's a micrometer dial on here, so you dial in just the amount that you want it to move to adjust the size that your fly cutter is or that your boring bar is making inside the hole. In addition to the square end mill that we looked at here, there's other kinds of end mills that aren't square, such as ball nose kinds, such as this one. So you can see it has that rounded tip for doing smoother cuts if you don't want that square internal cut. And there's some kinds with weird shoulders. There's some with different kinds of cutting profiles. These are just covered in wax because they're brand new, and so this is to protect the edges from chipping against the other teeth. As a note, if you have your own end mill and you want to keep it nice, you should keep it in some kind of a container like this so that it isn't hitting the other end mills and potentially getting chipped. So I'm just going to put this in one of the less full 1/2-inch drawers down here. Oh, and I actually saw one other interesting kind. So this is a roughing end mill. So you can see it has those teeth, and it leaves a not very smooth finish, but it can remove material more quickly. So sometimes that's useful. And I just saw this keyway cutter, which belongs up here. Okay. End mills obviously get dull after some time, which is why over there we have what's called a Derex end mill sharpener. And you can get badged on that tool if you want to sharpen the end mills instead of buying new ones. So that can obviously be a great way to save a lot of money because end mills can be quite expensive. So you can learn how to sharpen them and have a brand new edge to cut with. We're going to look at two things before we turn the machines on. One is oiling them. So they have a lot of metal surfaces rubbing against each other, so it's important to make sure that they stay oiled. The variable speed Bridgeport over here has an easier system. All you have to do is push this handle down, and it automatically squirts oil through these hoses all the way around the machine. So it's nice and oiled, except for the head. Up on the head, there's a little oiling cup right on the side here to keep that quill oiled. So you just squirt some oil down into there. Now we'll look at the other one. To oil this is a little harder. We have right here this lubing system, and what you do is you take it and put it into each of these little things called zerks. So you put it right on there, and then you push maybe twice, and it'll squirt the oil right into there. So there's one here. So right now we are oiling the y-axis. Now we'll oil the x-axis right here, and over here. And then the z-axis is here, and on the other side. And you should oil the Bridgeports at the start of every time you use it. At most once a day. You don't need to do it multiple times a day. Then the oil for going in the top, you can take this oil and put it right in this little, in this case, both of these little cups. So you just squirt it into there and into here. And it says oil slot weekly. So occasionally. So in terms of safety on these machines, before we turn them on, number one, you obviously never want to leave it unattended when it's running. So you need to make sure to stay with it. There are some automatic features on here. So if you engage those, you need to make sure to stay right by the machine. Then if you obviously need to make sure not to have any dangly neckties, earbuds, sleeves, jewelry, stuff like that. You know, something is spinning really fast here, it can make chips that can grab onto things. When you, obviously in the metal shop, always eyeglasses, and make sure to never be working on the thing when the tool is on. So make sure to turn it off before working on your workpiece, maybe changing the setup or anything like that. Maybe don't get your face too close to it. It can be tempting to get really close, but chips can come flying out. So make sure to keep your face a safe distance. And then there are, on this one, spinning belts up top. So you need to make sure when it's running, make sure your hands are nowhere near those belts, because that would be a whole world of not fun. And last, when you are putting your workpiece in, you need to make sure it is really well secured. So no matter what kind of work holding you're using, you need to be able to hit it with a dead blow hammer and see that it does not move after you've mounted it. Because if this is exerting a lot of force when it's cutting that metal. Imagine taking a kitchen knife and trying to cut a piece of steel. It's really hard, it's pushing really hard. So if it is at all loose, it's gonna come flying off and be really dangerous. We're gonna grab this indicator on a quill clamp. And then last, we're gonna grab an edge finder. What we're gonna use this for is we're gonna do like a cursory tram on this vise to make sure that the person who used it before us left it in a really good spot. If you move it, this is what you'd need to do afterwards. And if you were to move the head in any way, you would need to do something similar to make sure that you put it back in the same position. So this is meant to clamp right on our quill. So it goes just like that. And then we're gonna put this indicator on here. And I'm going to move our table back. And then sideways. And the goal here is to make sure that the vise is really straight. We always indicate against the fixed jaw because that's more accurate than the one that can slide. And we're going to angle this so it's pointed right there. Tighten things up so they don't move on us. And then we're going to do what's called preloading the indicator. So I'm going to go forwards until that needle moves a little bit. So we'll get it to say 15. And now I'm going to go sideways and we're going to see how much it moves. So it looks like it hit a little bit of dirt. And this indicator, the smallest graduations are 1/2 of an inch. So I just went across and it moved by maybe half of one graduation. So that's like 1/4 of 1,000th of an inch. So that's really good for what we're doing. So that is nicely trammed. Let's say that it wasn't. What you would do is take a wrench and loosen just slightly these nuts on either side. So 1, 2, or even maybe just one of them. And they wouldn't be loose, just like loosened a little bit. Then you can take a dead blow and just tap a little bit. So here you can see I'm hitting this and it's not even affecting the dial indicator. That's how nicely dialed in that is. But let's say it wasn't quite right. Let's say it moved over to the 10, so it was 5/1000ths of an inch off. Then you would want to move this side by 2.5/1000ths of an inch, so half of that distance. So you would tap, tap, tap until it got right to the middle, and then run back across, and hopefully it should stay the same. And you keep doing that by moving it half of the distance that the indicator moves until you get it so it's just straight. In general, you want the total indicated run out, or the total amount that indicator moves over the length, to be within 1 or 2 thousandths at the most, depending on what you're doing. So that's pretty good. We're happy about that. Let's say you were clamping directly onto your work surface, onto the bed, instead of using the vise. Then you might use this indicator to make sure that your workpiece is clamped perfectly straight. So that's how you'd make sure that whatever you're working on is straight, or up and down, or whatever was important to you at that time. Now, let's say that you had tilted the head and you wanted to put it back to a straight position. The way you would do that is by taking this and turning it into turning it to this orientation, and you would touch it against the table and see how much it moves, and then spin it around to the other side and make sure that it's at the same height. So that would make sure that it's perfectly straight up and down when the indicator reads the same on 2 positions on either side. If you tilt it forwards and backwards, then you would find 2 positions on the front and back of the bed to make sure that it's square that way. And then let's say you turn the whole turret sideways, then the way you get it back to 90 there is by running this indicator off the quill along one of these edges to make sure that it was perfectly straight with the bed again. The next tool I want to show you is this stone. So this is a stone for making sure that there's no burrs or things on here that are going to make your piece not sit flat. So first you would clean the surface because you want it to sit really flat. And after cleaning it, then you would just take the stone and go around a few times in a figure-8 pattern to knock off any burrs. You could do it on your workpiece too to make sure it sits totally flat. Let's say you had taken the vise off and were putting it back on. You'd want to make sure to stone the bed and the bottom of the vise to make sure they were going to sit perfectly flat on each other too. Now we're going to look at the edge finder, or a wiggle edge finder is used for finding the edge of a piece. So let's say we had our piece in here. First, we need to get a collet to hold this. In general, you want to use a collet anytime you can because the collet is more precise than a chuck. So the edge finder has a 3/8 inch shank. So we're going to grab the 3/8 inch collet, the R8 collet. And before we put it in, we want to make sure it's very clean. So I'm going to make sure to clean the edge finder. We'll grab the rag. Clean that. And then also we're going to clean the outside of this tool holder to make sure there's no chips on there. And we're going to take our finger and put it inside this and clean that out to make sure it's totally clean. There's no chips in there either. Then we're going to start by putting the tool in here. And you can see that keyway, that slot that goes right where this little set screw is. You're going to find it with your finger and then put it up in here and make sure to align the two. So this is aligned with that little thing, and now you hold it with your hand, with one hand, and with your other, you're going to push this in button. So this is a pneumatic system, meaning air powered. So the air is going to go through this thing called a pneumatic drawbar. In the old days, there would be just a drawbar, a piece of metal going up, and you would use a handle and crank it to turn it, or your hands, and that was kind of a pain in the butt. So now we have this pneumatic system. So to put this collet in, we're going to put this here, and we need to make sure that the quill is all the way up. So we're going to loosen that, and then slide the quill all the way up. And now push the in button, and now it's holding on to that. So it's just like a drill that's screwing down on the drawbar to pull that up in there. You never want to tighten down on the collet with no tool in there, because that'll deform it, it'll squish it. It needs to be holding on to something. So we'll slide our edge finder in there, and then in, and now it's nice and tight. You can bring the Z up or the quill down. In general, the more that this quill is sticking out, the less accurate you are. So you want to, when you can, bring the knee up, bring the workpiece up to the tool, and then just use this for drilling operations when you're going down into the workpiece. So now we're going to turn the machine on. We want to make sure it's at the right speed. And for the edge finder, you want it to be about 1,000 RPM. So we'll look on here, and 1,000 RPM looks like it's at the second pulley down from the top in high speed. So that's where we'll put it. So it's obviously off. We're going to loosen both of these and move it closer. And then we're going to the second from the top. Okay, so now in the second to the top pulley, so I'm going to re-tighten that head and tighten here. And now we want to be in high gear. Right now we're in low gear, so to get to high, like we said earlier, we're moving the A, this one, to the front position, removing this, it's already in the low position. We're going to move this until it drops down, which it just did, and then move B, this guy, to the high position. So now we're in high gear, and this guy is going to move fast. I just grabbed this piece of scrap aluminum that we're going to use as a demonstration piece. So I want to clamp it in the vise, and I want to have a good amount of it exposed. So I'm going to grab some parallels, and we're going to wipe them off. And we're going to wipe off inside the vise to make sure there's no chips or things in there that are going to mess us up. gonna take our workpiece, we will orient it like this, snug it down a little bit, and grab the dead blow, give it a whack, and now you can see that the parallels don't move, and then I'll just tighten it up the rest of the way. Then we're going to use the edge finder to find the edges of the piece so we know where we're cutting from. Alright, so now that the workpiece is mounted, we want to find the zeros, meaning find the edges of our workpiece, so it can be zeroed in the DRO. So we already set the speed to about 1,000 RPM. We set it to 1,115, so we're gonna come up to the edge. Looks like we need to drop the knee down just a little bit maybe. And because we're in high gear, we are going to move the handle forward to the up position when we want to turn it on. We're gonna turn the machine on, make sure the E-stops are not engaged. Now the tool is on. And I'm going to push forwards to put it in high gear. And you can see that the edge finder is just wobbling around. So what we're going to do is get closer and closer, and eventually it'll wobble a little less, and then it'll not wobble, and then it's going to kick off to the side. I'm going to go really slowly, just like that. So if you come here, you'll be able to see it better. So it just deflected off to the side a little bit. So we're gonna turn this off, and now we want to tell it that we found the X0. However, this is offset a little bit because our edge finder has a thickness to it. So the diameter is 0.2 inches on that edge finder, so it's off by 0.1 inches, and it's in the negative direction. So we're gonna go over here, and we're gonna click X, and we're gonna tell it that it is 0.1 negative, enter. So now it knows that that's the position. We're going to do the same thing with Y. So I'm going to come off that a little bit so we don't smush it, and then go to the front face. Go over here, turn it on, and then come right up to the front. I think it'll look better if you look at it. Until it stops, and then get ready, just like that. So it kicked over, and now we can turn it off. And for the Y position, we're going to tell it Y, 0.1 negative, enter. And now for the Z, we do it a little bit differently. We don't have a Z edge finder, we just use a shim. But you're going to do that with the actual cutting tool that you're using, because we're going to replace this edge finder. The X and Y don't change when we put a new tool in. The 0 is still set right at that corner. So now what we can do is just drop this out of the way, because we don't need it in our faces anymore. And we're going to grab an end mill. So because this is soft aluminum, I'm going to grab a 2-flute end mill, and we'll just grab a 1/4 inch end mill. So here we have a, this is a 2-flute end mill. So you can see 2 flutes, it's center cutting. The flutes go all the way to the middle, and it's 9/32 of an inch. But the shank, but conveniently, the shank of this that the collet clamps on is 3/8 of an inch. So we can just keep the same collet in there. So I'm going to remove this. We need to make sure that the quill is all the way up, and then put your hand underneath here so it doesn't fall. Push the out button, and then you can, it's a little sticky. There we go. Slide our edge finder out, and slide our tool in. Again, making sure it's clean. Right up in there, and then in. And it's nice and tight. You don't need to go crazy with that. And now we can do some cutting. So we need to know how fast we want to cut, and there's a formula for that. The formula is 3.82 times the cutting speed, which we get from the handbook, you'll see in a minute, divided by the tool diameter. The cutting speed is measured in surface feet per minute, and that 3.82 is a calculated number that you can look up how it's calculated. We'll look up the number so you can see how it's done, But in general, determining the speed, which is how fast this spins, and the feed, which is how fast you crank on here, on a Bridgeport, is much more of a sort of, you get a feel for it. So when you're using a Bridgeport, it's important to have a good sense for, say, you're using a larger diameter end mill, then you need to go slower, or a smaller diameter, you need to go faster. In machining, there's a Bible called the Machinery's Handbook. This is the abridged version, and then this is the big full version. And this has every piece of information you would need to know to be a machinist, but we often just open it up for little bits of information. So here, bookmarked, is a table showing you various speeds. So this table are the speeds and feeds for plain carbon and alloy steels. So in the light metal table, we're looking at aluminum alloy. I don't actually know which aluminum alloy it is. We are milling, so it says the cutting speed in feet per minute using high-speed steel, which is what we're using, that HSS, is somewhere between 500 and 600. So if we take that formula we had, so we're going to do that 3.82 times the 500 we found, divided by 0.25, and you'll see this gives us a crazy high 7,500 RPM. The Bridgeport can't go nearly that high, and the takeaway from that is that we can go really fast. We'll have the machine go fast, but then we'll just feed, because we know that the Bridgeport isn't, the speed isn't that high, we'll compensate by also reducing the feed, so we'll go a little bit slower. If this was on a CNC where you could go that high, then you could accommodate that speed and have a really high feed and remove material really fast. But let's say we were wanting to make sure we were going exactly by the book, then we would want to know the RPM, which we calculated, and how fast we're feeding, so the speed and the feed. And the feed that we're moving at, measured in inches per minute, is calculated by taking feed per tooth, which again we get from the handbook, the number of flutes that we have times the RPM, which we calculated. So on this page, we can see the recommended feed inches per tooth for milling with high-speed steel cutters. So for aluminum, we're going to go over the depth of cut of about 0.05 inches. And then the cutter diameter is about 1/4 inch. And it says that we should, going down, have a feed per tooth of about 0.02. 0.002 times the number of flutes we have, which is 2, times the RPM we found, which was about 7,500, and that equals 30 inches per minute. So that is pretty fast. And we are, but like bear in mind the depth of cut there was relatively small. So, but that's how fast you would move. So there are also lots of calculators online where you can just plug your numbers in and it'll tell you how fast you can move. Also, if you buy an end mill, it'll often tell you when you buy it, the chip load, which you can put into the calculators and it'll tell you how fast you should go. But again, on the Bridgeport, in general, you're just kind of doing it by feel. If you see lots of smoking, or if you're cutting steel and the chips are coming out like blue, then you know that you're going too fast or too hard. You need to cool things down a little bit. If you're dulling the end mill, or if it's melting the aluminum, then like you're also going too high. But if it's bogging down, you might be going too slow. So it's kind of just like getting a feel for it. So here, right now we're set at 1,000 about RPM, and we're gonna give that a try and see how that works. So we have the tool loaded, and what we want to do is to set our z-axis so we know how deep we're cutting. So I'm going to take this parallel, and the parallel is 1/8 of an inch thick, so 0.125. We're going to set it on here, and I'm going to bring the table over, and then up. And we don't want to hurt the parallel, so what I'm going to do is just gently bring this down and lock it, and then really slowly bring up the z-axis while I'm moving the parallel until I see it grab. just like that. So now we know that over on our z-axis, we're at 0.125 above the workpiece. So we're going to set z and 0.125 enter. And now we can come up off of it and remove this guy. And then now when we go to make a cut, we know how deep we're going. So we'll go over here, and there's two, well, you can cut with a slot, so if you go right down the middle of the piece, but if you're cutting on a face, then there's climb and there's conventional cutting. So if we're going this direction, you can see that these blades are pushing against the aluminum as we're cutting. So if we're cutting in this direction, so cutting this direction with this spinning this way, they're opposing each other. That's called conventional cutting. And on the Bridgeport, that's what you should do. You want to be cutting in conventional. And the reason for that is because inside the ways we have the lead screw, just like this, but down inside, that's controlling the axes. And you want to be pushing up against those screws. If you go the other way, so let's say we start cutting this way, which would be going climb cutting, then these blades start to climb up on the aluminum. And what that's going to do is it's going to take it and it could move the table a little bit along the backlash of the screw, and it could mess up the piece and potentially hurt the machine. So basically the takeaway from that is you always want to be cutting conventional. So that means cutting just like you would on a router. If you're familiar with woodshop tools, on a woodshop router, you're always cutting conventional. You're always making sure that you're pushing in opposition to the direction of the movement. So here we're cutting in the opposite direction that we're moving in. All right, so we're going to take a conventional face cut right along here, and we're going to set our depth of cut. So we know that this is a 1/4 inch end mill. And so if we have on the DRO in the y-axis, if we were just 1/8 of an inch off, well, we wouldn't be touching it at all, because that would be it's just at the edge, so 0.125, we're not doing anything. So let's go to 0.11, right about there. And now we know we're taking 15 thousandths of an inch off of our workpiece, just like that. So since we're moving in the x-axis, we're going to lock the y. So I'm just going to turn this to lock down so it can't move. You could get an Allen wrench if you really wanted to lock on it. And we're going to turn the machine back on, deactivate the e-stop. And we're going to put a little cutting fluid on it. So for aluminum, you can just use WD-40. The purpose of the cutting fluid is it helps to lubricate the chips so that they can get removed more easily. Especially aluminum can get gummy when it's hot, so they can help with that. It can also help to move the heat and to keep things nice and cool and happy. So if you're having problems, one easy solution is is cutting fluid. For aluminum, WD-40. Over here we have some other oils that you can use for steel. All right, so we're going to turn it on and taking a cut. And as you can see, it's just by feel. So if I go slowly, you make little teensy chips, and you can see it kind of gumming up on the end mill if you get close. And you don't want that, because that means you're going too slowly. It's just getting melty. So I'm going to go faster. If I go too fast, you can hear chattering, and it'll leave a less good finish. So I'm going to go to medium speed, and that's what I mean. You just kind of get a feel for it. And so that's probably the best speed right there. It's giving a really smooth finish. It sounds happy. There's no smoking. So that would be a good combination of speeds and feeds. So we're going to turn you off, hit the brake. We're going to look at one other thing on the other Bridgeport. I'm first going to turn it on. And here, a few differences you can see. One, the vise is not attached. So if you were using this and wanted to use the vise, you need to reattach it and tram it. Two, the table's much longer. This is about a 4-foot long table. So that's really nice for bigger pieces. And it being so long, it takes a while to crank it all the way along. So here we have a power feed. And so here, you just move this handle, and it automatically moves itself. And when it gets to the end, it'll automatically stop itself, which is great. Here you can set the speed that it's moving at. So it's at fastest right now, you can slow it down. Let's say you're doing a long cut and you didn't want to be cranking by hand. You can set the feed you want it to go at and it'll consistently do that feed. So that's really nice. Let's say you wanted to jog, which just means moving quickly to a position without actually cutting. You can push this button and that'll go fast. Once it gets to the end, slowly, you'll see that it'll stop itself automatically so it doesn't hurt itself. Just like that. And then I'm going to send it the other way, just so we get it back in the middle. One other thing we're going to look at on this machine is the quill feed. So the quill feed allows it to feed down automatically. The way we engage the quill feed, it says right here, is stop motor to engage. So it's important that you don't want the motor going when you engage it. And then disengage the quill feed when it's not being used. And you don't want to do the quill feed above 3,000 RPM. So right now it's disengaged, it's to the left. To engage it, we move it to the right. So we're going to pull this out and go to the right. And it doesn't really want to go in right now, so we're going to turn. So we have the quill feed selected in the right side. So now it's engaged. And then we're going to go over here and look at this side. So there's 3 numbers on here: 3, 1.5, and 6. So that is the thousandths of inches that it goes down for every rotation of the head. So let's say you set it to 2,000 RPM, for example. Then for every rotation, it would go down 6 thousandths in the number 6 position. So we'll put it in 6. And then we're going to turn the machine on in high speed. And then to engage it, we're going to push this in. So you can see this spinning. And then we pull this handle. And you can see that handle coming down and the quill extending. So that's pretty good. So that is how you would do a nice even feed down. Then you could go the other direction. And here's neutral in the middle, and all the way out is now feeding up when you engage it. So that's pretty great. When you're done, obviously turn this off. You can bring that back up, and then disengage the quill feed so the next person isn't really confused. Now last, when you're done using the machine, you need to make sure to clean up, all the way clean out the T-slots, vacuum it off, make sure to put everything away. On the side table, we should only have the parallels, these clamps, the brush, and some oil. We don't want other bits and pieces in people's projects and whatnot. Put the parallels away, make sure to clean up all the chips, like I said, brush everything off, vacuum up the floor, so it's really nice for the next person. Thanks for watching.